Go ahead.
Folks, welcome to this HAO colloquium. Today's speaker is Shahida Begum Sheikh, Shahi for short, and she works as a postdoctoral research fellow at the U.S. Naval Research Laboratory and George Mason University. She's from the WHISPER heliospheric imager team of the Parker Solar Program, and her research mainly focuses on understanding the underlying physical processes of coronal mass ejections and solar flares utilizing multi-wavelength observations. She got her doctoral degree from New Jersey Institute of Technology under the supervision of Object Theory in 2021. And her dissertation is on the topic of, or was on the topic of solar flares as observed in low frequency microwave gyrosynchrotron emission using the expanded Owens Valley Solar Array. While she was at NJIT, her experience in India included testing and calibrating X-ray detectors on board of Ionosphere and AstroSat satellite projects, and also interplanetary scintillation radio observations. Currently, she's working on studies of the internal structure of CMEs, magnetic island-like features observed by WHISPER, and correlating in situ and heliospheric modeling measurements, as well as source morphology analysis of flares observed by the OVSA, the expanded Owens Valley Solar Array. Welcome, Shahi. Yes.
Thanks so much, Sarah. Hello, everyone. So, as Sarah said, my name is Shahida Begum Sheikh. So, in this talk, I'll try to give the studies that I have been doing for a while, and also the ones that I have done previously. So, I'm not sure how many of you are from solar flare background with radio physics, actually. So, but I'll try to give the little bit context of the analysis part that I have done. And also, I know some of you were in a Punch meeting last week with my talk, so please bear with me when I'm using the same slides last week. So yeah, so let's. So with the outline, I have 4 different studies, which the first one is solar flares as observed from microwave emission from EOPSA, that is expanded Owens Solar Array, and the second part is from CMEs as observed from white light observations from WHISPER partial probe. So for solar flares, I will try to focus on these 2 main studies. One is when EOPSA has gone through. EOPSA is basically a radio interferometer. So it has gone through an expansion phase in the last 1 decade. So we started to have the data coming in from 2015. So the first part of this, the flat optical lithic study is done when the imaging observations were not available. The first part basically focuses on the spectra, only the spectra of microwave emission. And the second part is to understand how the solar flares look like in microwave imaging observations. So we know that in general, when a solar flare happens on the surface of the sun, usually it takes place somewhere like that. In this example, 2-dimensional standard flare model. And during the process, enormous amount of electromagnetic radiation comes out. So as an example, from RESI spacecraft, I can play this movie to quickly demonstrate how it looks like. For example, if you're looking at the soft X-ray emission, so this loop is illuminated, and the hard X-ray emission is seen at the points of that loop, and over the white ribbons, which are also seen in H alpha, and these are the post-flare. Yeah. So these are the loops which are formed in after the reconnection, called as post-flare reconnection arcing, are seen in EUV. So if you see the same scenario in microwave observations, which are kind of rare, but currently we are starting to have that from EOPSA, that is expanded Owens Valley Solar Array. So when we see the same scenario in microwave emission, what happens is the particles get accelerated in this. Do you see my cursor?
Yes.
So when the particles are accelerated, they get trapped in the magnetic field lines and they gyrate in the magnetic field line, which creates the gyrosynchrotron emission or the microwave emission in gigahertz of frequency. So when we see those microwave emissions, they basically cover up this whole flaring region at different parts, like somewhere at the foot point, sometimes the loops, at the top of the loops, sometimes closer to the current sheet itself. So, so that is a two-dimensional picture of a flare model. So there are a few studies, once again with radio, like Hanukkah 1997 and 1999, have used radio observations where they have seen double sources like this near near the legs of the loops. And they came up with this scenario where instead of having just one loop which is expanded and getting reconnected, here we have two loops which reconnect and give rise to multiple sources as what we see here. So at the time, the radio observations were not very clear, but still with that came up with this graph. So just to give you a context for microwave observations, so it can be done either in brightness temperature and also flux density observation. So when we look at the spectrum, I'm not going to talk in detail about it, but if we look at these parameters like density and magnetic field, the shape and width of the spectrum changes with the changes in those physical parameters. That's what we see here. And the main point that I want to bring up is this 2.9, which is the power law index in the optically thick side of the emission with frequency. So that basically directly indicates the size of the source from where this emission is coming from. So I'm going to emphasize that. So, so this 2.9 is a value where it's a theoretical value when we assume that the emission is coming from a homogeneous source, in a sense, one single source, one uniform source. So, but reality, what happens is when we look at the observations, that slope is not 2.9, but it's 6.4 sometimes. Sometimes it's 0.2, something like that. It's much flatter like that. So we'll talk more about that. And now if we are not looking at the spectrum and if you are looking at the images, so I used one of the examples, recent examples here, to show you how the microwave sources actually look like. So this is the same loop which I showed in the first slide with the standard flare model. So the loop in which is going through the reconnection, and with time we see that how the sources are spread out on the loop. And also the second point is look at the frequency with frequency, higher frequency blue, lower frequency red, and if you see how the source sizes changes with frequency. So size of the source increases as the frequency decreases. As you see that the red one is bigger than the small one. So that is just to give you a context. So in very rare observations like these, where at low frequencies, in the sense, if we talk about less than 10 gigahertz of frequency, 1.4 or 5.7, there were few very rare observations which have shown us when we take that power law size, power law index of the source size with frequency. So these sources kind of deviate from that size itself. So they are much larger than what we expect to see. So in this study, we are going to understand how those sources are big and what makes them big. So these are only the very few observations as we have, but recently EOFSA has started giving data. So what we did is in the first analysis, without having images at all, so we did spectral analysis of 12 bursts, in the sense 12 solar flares, and we get the radio burst. So what I have here is a three-dimensional representation of the radio emission. And if we just take 11.3 gigahertz, so if I take a cut here, so this is what profile looks like. So in that profile, if I take 5 different times, and if I plot the spectrum, this cut, vertical cut is basically that spectrum. So this is the same thing which I showed previously for the three theoretical value. So as we see that with time, we know that the intensity increases and then decreases, which is obvious. But one thing that we can observe here is that spectral index value, alpha L, is 1.27, and it goes all the way to 0.25. So which is quite different from what we expect theoretically around 2.9 value. So now what we did was same analysis if we conduct them on all the 12 events or the 12 solar flares or the bursts. So if an spectral index for 3 different times, rise, peak, and the decay, and take those values and compare with the theoretical value, what we see here is almost 5 of the events here have much smaller than 2.9 value means, and we call them as flat spectrum. So which is basically indication that the source is not homogeneous. It has to be inhomogeneous nature. It has to be very non-uniform type of emission, which should give a flat spectrum. So we will scrutinize that in a moment. But that is the initial observation that we get from the plot on the top. And the other one is if we see that the spectral index in many of the bursts, like 9 out of 12 bursts, the spectral index value reduces from the peak to decay in almost 9 of the bursts. In the sense, but do you guess what it is? It's basically as the time progresses, the complexity of the sources is increasing. The inhomogeneity is increasing in those all the 9 bursts. So now let's look at different exercises we conducted to understand why it is large, why the sources are large, and are they really large, and why are those really inhomogeneous in nature. So there's a simple equation which shows what is the flux density with frequency looks like. And here are the different, K is the Boltzmann constant, nu is the observing frequency, C is the speed of light, dV is the brightness temperature as a function of frequency, and sigma is the solid angle or the area of the source itself. So now having that simple equation, and we know S, which is the observation itself, the flux density, but we don't know the brightness temperature at the time. So what we can do is we can just assume a very high value for high threshold for solar flares is until the 8 Kelvin and put that in this equation. So to just balance that equation, if this value is much bigger, we expect this solid angle to be smaller, right? To balance that equation, just a mathematical calculation. So what we did was we took that higher value and we plotted the source area, that is the sigma, as a function of frequency. And what we should expect is the sigma to be much lesser. But what we see here is at that higher value, we still get a bigger value of around 6,000 arcseconds of area at that low frequencies. So what I did was just to have a visual understanding of this plot. If I take one cut of that and get the diameter of that size, and this is how it looks like for the regularly observed radio and RESI observations. From over the decades, we have been seeing these Nobayama and RESI observations. And if we take that for this particular event and compare with the EOFS observations, we see that it has to be much bigger than the usually observed sources. So it shows that it's a large source. But if we take this in reality it might be a smaller value, and then size will be much bigger than what we have seen here. So the next exercise that we did was relative visibility analysis, as the name visibility in the sense it's the way how the radio interferometer gets the data. So the name, the data that we get from the radio interferometer is called as visibility. So relative visibility is basically what we take is basically the ratio of two different kinds of data points from same instrument. So what I have here is V naught is basically from one antenna, one radio antenna. VS. So VS is basically from the whole interferometer, from all the baselines. Baselines in the sense distance between two antennas. So if we combine the whole, we have like 13 antennas. So if we combine all the 13 antennas, we get the data, visibility, VS. And in the denominator, we have just the visibility from one antenna. And if we take the ratio, and if we take the baseline, the smallest baseline, the smallest between two antennas, and what we get is just one, right? Because the smallest baseline is small, and the antenna itself is also small. So when we get that visibility data, and we take a ratio, we get one. Now, instead of that, if we take a bigger baseline, the whole interferometer, and take the ratio, that ratio will deviate from 1, it goes to 0. So what we did was, not to go into much of the details, but I will quickly show you this plot, which is basically the right-hand side, relative visibility on the y-axis, and B lambda is the baseline length on x-axis. And if we plot that, what we get is that blue points and the slope. Slope is basically is for a straight line, it's y is equal to mx, and the rest of the parameters are basically slope, right? So from that slope, we can directly get a proxy for the size of the source itself, which is d. So from that slope, so here, for example, I have 6.91 frequency, and if I do that for all the frequencies in the observation, I get these points, the green points, which are basically the sizes measured from this exercise, relative visibility. So, and at that point, this is a famous 10th September 2017 event that everybody was going crazy, and they did observations on that. They did studies on this EOS observations on that event, 10th September. So I took that as an example, and as we have the imaging information for that event, we got the full width maximum size of that and compared with this relative visibility. So if we see that they match well at the low frequencies very well, right? So that shows that this relative visibility can be a very good proxy for the solar source size itself. So having verified that, we took the same analysis done on the flat spectra, so that I have shown previously. As we don't have imaging information, just having that spectral information. And we had lesser baselines, but still we got a very good trend of the source size with frequency, as you see here. And the very important point that we can note here is at low frequency, for these only for flat spectra, we see a size of around 100 arcseconds of the source size for all the flat spectrum. So when we see them do the same analysis on non-flat type spectrum, we get much lesser value of sizes. So this is a direct indication that the sizes of the sources when we see a flat spectrum are bigger. So that is one conclusion. And the second conclusion is, in reality, there can't be one uniform source on the sun, right? So it has to be inhomogeneous in nature. So to support that, we took these ad hoc equations, which depends on the magnetic field magnetic field strength, and I are the different components. So what I have here is the very simple comparison between observations. The stars are the E observation, and the black is the model fitting. So in order to get the best fit for the data with that black curve, we definitely need seven components. So let's say 0 to 6 different components. If we just take only 2 components, let's say 0 and 1, only the high frequency part is fit. We don't see any fitting done at the lower frequency. So what it says is basically, so that source has almost 7 different kernels within which are giving different types of emission to make this spectra, instead of being steep, makes it flatter, so that all the emission from that are added up to make it look flatter. So in conclusion, we would say that at those low frequencies, without having imaging information, just by having spectral data, the source is bigger, of more than 100 arcseconds of data, 100 arcseconds of size. And second one is those have simultaneous multiple emission within that source, making it inhomogeneous. Also, we see that as the flare progresses, the or increases, the complexity of those sources increases. So that is without having imaging information. So luckily, in 2017, we had this event, which turned out to be a proof of concept, something like that. So with whatever we have done the previous study, so we have seen here in this event. So I would quickly tell you what we have here. So these are the different frequencies: 3.44 and 7.44 gigahertz, 13.44 gigahertz, different frequencies. The background, we have AIA, UV observation. And this is the spectrum where we have the white line, vertical line. Basically, it runs through the spectrum. And as it runs through, you can see how the sources evolve in each of those frequencies. So I would like you to compare this higher frequency, the lower frequency, and see how different the sources are. The line goes to the peak. Look at them. So what we have there is basically the same. So I just took some screenshots from the same movie. So what we have there is basically at high frequencies, most of the emission are concentrated on the UV. Now the place where we see most of the UV emission are visible. So, but if you look at the low frequency side, it's much larger in the sense, if you compare this blue contour with the white contour, I would say it's 10 or 15 times bigger than what we have been seeing so far from over the decades, right? And also we see not only it's large, it also has this discrete sources within like that. So now so that is basically a proof that for the previous study, so it's large and also it is inhomogeneous in nature. So we have multiple sources within. And now what we did was having that confirmed. So there are few studies done previously to understand how the full width half maximum size or the area of the source changes with frequency. So in these observations, you see that the frequency is taken for the whole frequency band, in the sense 1 to 20 gigahertz of microwave radiation. And you see the spectral index -2 here, and here it's -0.5 to -3.5. And what I have here is basically, if we just take the full width half maximum, which is close to the 50% contour, so we have both low frequency 3.44, which is white, and green, which is 13.44 gigahertz, and for both the 10 and 50% contours. So you see that how different they are. So at high frequency, 10 and 50 are still dominated at one main site location, right? But if you look at the low frequency, the 10% is much bigger, right? So we have that comparison plot. Now, if we look at the power loss fitting that is used to make this, so if we just take like 50% contour or the full width half maximum, take source area and with frequency to get that value of whatever value that we want. And if we do the fitting for all the frequency points, that's what we see here for 50%, the red line is the fitting. If you see there is 0.8, right? So somewhere in this range, 0.8. So now we have seen in the movie that this high frequency and the low frequency are much different. So as they are different, if we fit them differently, like solid is for low frequency, dashed is for high frequency, we see that they still show much different values. So what we would say from that is, just by taking one frequency is not a very good idea to get that relationship, power law relationship. What we need is, first one is right contour. Why? Because if you just take 50%, we are only taking that part. We are missing out this whole big emission of the source, right? So when we consider the 10% contour, we see that power law index values are much different now. So the red line, it's -1.6. Previously, it was 0.8. So the main points that I want to make here is, when we make such a power law relationship, it's important to take right frequency batches or low frequency separately, treat them separately, low frequency separately and high frequency separately. And also the contour levels are pretty important. So because if we just consider the full width half maximum, we're going to miss out the rest of the emission. So it's important to take 10% or whichever level we can go down to. So that's one point. And now, not to bore you guys, now let's look at the images now. So here we have EUV observations. So as the movie shows that these are the multiple loops which are getting involved in the flaring process. So I have just numbered them visually. And then here we have HMI magnetogram, which gives the magnetic configuration of the active region from where the solar flare is coming from. So on the top, we have EOPSA emission. So this black box is basically that box. So when we do the magnetic field extrapolation on that black box, so we see that this C-shaped negative polarity has connections from here all the way to the other side of the active region. And also there are tiny flux loop systems beneath them. So how does it look like? Is basically one on the top, which is the large loop system, and one here hidden in the backside, which is the smaller loop system. So now if we try to treat them separately, all the four sources that we have, S1, S2, and these secondary sources, we will get some understanding of how particles are getting accelerated, how they're getting transported to different locations, all those things. So what we did was we treated all those four sources separately. We took those boxes and we got the intensity from that or brightness temperature from those. And if we simply plot them with time, so what we see that is S1 and S4. So these are the black and blue curves, which are almost look similar to the light curve itself, the time profile itself. But if you look at this green and red, they have the peak is delayed almost like 15 seconds from the previous one. So what it says is basically, so that time delay is the time taken for the particles to get accelerated and to get injected and get trapped in that magnetic field lines and travel to those remote locations, S2 and S3. So you might have got this idea that these remote sources have already seen in previous other observations. But these are not the remote sources. These are the sources within the active region itself. In previous, some of the other studies you would have seen where there are sources which are created from very far away from the flaring region, but these are not those. These are within the active region where we have seen discrete emission, as what we see here. Having all that in mind, I came up with this cartoon, a simple cartoon. So if you remember previously, we had this simple two-dimensional standard flare model. So what we see here is that type of flare model is happening in that smaller loop system. But as you see in upper side, it's a big dome formed by those large overlying loops. So we have also seen a filament which is getting erupted, but it fails to erupt out. It falls back. And it might be due to the reason that filament is somewhere there. It erupts out, but there is a dome structure which constricts it and it falls back. So, but the point is when, as we see the two peaks or the two different system of sources from this main site, where we see most of the emission, like hard X-rays, H-alpha, UV, are seen only in these regions. But in these secondary regions, we don't see any signature of other wavelengths. So that basically shows that those are the collision rate required for the other emissions to take place. But here in microwaves, we have that capability where we can resolve the sources and we see that the particles which are getting accelerated at this deconnection site, taking time to travel and reach those other locations as what we see in the second. Thanks. So basically this say that there is a sequential reconnection taking place, and second one is transport of accelerated particles to the other end, and where we do not see any signatures of other wavelengths. So in summary, the question is, whatever the event that we have seen now, does it support this two-dimensional flare model? The answer is no, because we really need a three-dimensional type setup to support what we have seen in observations. Why? Because we have seen multiple loop systems which are getting tightened up, and we have secondary sources seen in microwave. It supports that there is a loop-loop type interaction or 3D type model. And also we have seen that the accelerated particles in this kind of flare show that they have an access for the multiple locations of the flaring region. So that is about flares. Now I'll quickly jump to the CMEs part. So so far we have seen solar flares on the sun, and the observations are from the ground, EOFSA, radio, those things. And now we are going to the space to see how the CMEs from those, like we have seen how the eruption takes place on the sun, right, with solar flares. So whatever is getting erupted is seen as a CME, and Parker Solar Probe has a whisper imager onboarded. So it has taken some observations, which I'm going to talk in this study. So in general, people, when we see CMEs, we see this bright core and the front, and also, bright front, core and the cavity. So here an example which is seen by whisper images where we do not see almost the same scenario, but what we see is those nested ring structure. So they are the circular shapes here, and you see that they are all nested one on the top of each other. So we are trying to understand what those rings are in this study. So there are some previous studies which have shown how rings are sitting on the top of the sun's surface, like on the top of prominence like this. And some of the observations from Glasgow has also shown us those rings. So, but they are still rare. And now let's see how they look like whisper, and let's try to understand. So what I've done here is basically take different observations. One is stereo, SOHO, and Parker, and we fit that with the CME model, GCS CME model, to create the flux rope itself. And yes, please.
The image you took on the right, is that a running difference, or is it just direct from this? The Parker.
This one is not a difference. It's a wavelet processed image, LW processed image. So the one which I showed here is the running difference. So this one is the running. As you see that, you see that black and white features. Those are from the running. So now to have a comparison, we have all these three observations. We fit with the model and with the croissant, and in the bottom we see how the model image can compare with the observation. They match very well with the observations. So we want to understand what these rings are and are they real and why we don't see them in other observations. Because if we imagine that all the CMEs have flux ropes and all the flux ropes have this nested structure, we want to make them as a comparison with other instruments with the same particular CME. So what I have here is whisper and stereo images in both of them. So one is with the default basic processing, another one is with the wavelet processing. It's a I would say alpha processing of stereo images. So what we see here is in the default processing, we don't see those rings as what we see here in this project, right? So, but when we do a little bit more processing, even then, what we see is that circular friend, but still it couldn't resolve those rings or the details of the CME that we see here in this one. So now if we compare them with respect to different parameters, so what I would say is in order to see such nested structure, so what we need is these conditions. One is to have a good viewing angle. So here I would say that this CME, if it is not seen as what seen here in Whisper, if it is in some other angle, I'm sure that we would have not seen those rings, right? So we really need a good orientation to see those rings, first thing. And second one is good resolution of the instrument and good sensitivity. So if we ask about the resolution of the instruments, Whisper and Stereo both have almost the same resolution. But thing is, Parker Solar Probe is traveling very close to those features when compared to Stereo. Right? Stereo is almost at 1 AU, and where Whisper is at 0.18. We are almost like 1/10 of the distance closer to the feature, so which makes us see those structures. And second one is other one is exposure time, and also I would say Thomson efficiency and white light integrating effects. White light integrating effects in the sense, we know that as we are looking at the white light observations, we are integrating with the line of sight. So when the feeder is moving, so as it is optically thin emission, where we are integrating the structures in the front and in the back. Right? So as we are in the farther distance for stereo, we are integrating all of them, which makes them look something like blurred, what we see here. So so having all those conditions, we would say that, so when something fulfills all these conditions, we can easily see those rings. And now the other question is, whether we make a connection of these nested rings to the source region itself or not. So for that, we don't have a very good robust data set to make that correspondence between the rings seen in CME and the rings seen in pre-eruptive setup. So I would just show some few examples with Whisper in 2021 November. We see those rings here. And also in Glasgow, there are many other examples where I've seen such rings as well. The second part that we see for these nested rings is coherency. So are they moving with as one coherent structure, or they are moving as different system of loops? So just by taking 4 different points here and plot the x distance with time, we see that all of them have the same, almost the same slope. In a sense, show that they have the same speed. And we see some of the jumps here and there, that those are just because of the deformation that happens for the CME. Another one is the unwinding nature that happens here in the last loop. That's this jump. But other than that, we see that all of the 4 points have the same slopes, which basically shows that they have a coherent behavior. And also back here, what we are doing is just the plane of sky measurements, right? So the CME might be moving towards the spacecraft or away from the spacecraft. We don't know that, right? So for that, we are trying to get the projected velocities of that. So in this figure, what we have is the sun. So this is the feature that let's say this is the CME, and this is the Parker Solar Probe. And if the feature is moving a little bit towards PSP, so this angle can basically judge whether the feature is coming towards us or further from us. And also, but just by having that, we can't get the actual longitudinal extent of those rings. So what we are trying to get is the projected velocities and see how each one of them behave differently. So that is still in progress. Now let's look at the ring morphology itself. So in previous studies, flux flow or the in situ observations have shown us that when a magnetic cloud or the ICMEs travel cross over the spacecraft, so they came up with this contour, which basically shows the magnetic structure of the flux flow itself, something like that, which is axial in the center and tangential over the outer surface. And on the other scenario, flux tubes, so if we take a cross section of this flux tube, basically shows the rings, right? And here in the other scenario, where if you have a two-dimensional projection of a 3D structure, then also we can see those rings. So having taking those two scenarios in mind, what I came up with those two modeling with GCS cross-on fitting. So we took different flux ropes, one with it inside, just to create this nested structure, like a magnetic structure, and then see what the synthesized images look like. So now we see those rings in it. So on the second side, on the right-hand side, what we have is, instead of having nested rings, what we have done there is shift those rings inside with longitude in the backside. So basically the height of the flux tubes are shifted with longitude on the backside. So basically they are not all nested to each other, but they are little offset to each other just to recreate this flux tube scenario with projection. So even with that scenario, we see that there are nested rings within. And so those two things actually show that in the observations, as what we see, can be an effect of both the cross section or the internal structure of the flux rope itself, or it can be just the projection of the helical flux rope as what we are seeing here. So those two can also create such features which we are seeing here in observations. So this is another modeling that Tim Howard and Craig has developed. Let me play that movie. So basically it shows how the simple flux rope can reproduce the observations as what we see here. So with GCS, what I have done is that, so this is the legs of the CME and this is the cavity. So I created multiple such flux ropes to recreate those models as what I have shown here. But here it changed my perspective a little bit, where instead of having that, having this scenario, if we switch it a little bit, if you keep looking at these strands, so they are here and the other strands are on the other side. If we bring that to one such orientation somewhere there, we start looking at circular rings. So basically that fulfilled a few points which have not taken into consideration when I did the GCS modeling. In the sense, if you look at this V-shaped structure that is seen here in the observations, so that I don't see in GCS very clearly. And also the other one is these crisscrossed herringbone type structure is seen here in the observations also. And other one is, as I moved this model a little bit, you see that these are the semicircular shapes which are at one point getting merged to make it as a one circle. So in observations also, I don't get a very clear circle like what we have to expect, but it supports this model where it's just the projection of two semicircular shapes and makes it one circular ring-like structure. So we are still trying to understand this, but so far I just want to bring that for your attention. So there are such many scenarios where we can still see rings, for example, here, and somewhere here. Yeah, so there are many orientations where we can still see rings, and the internal structure of the CMA changes depending on what we are seeing as well in the model demonstrates. So in our previous bunch meeting last week, so we had this discussion about the plasmoid. So I tried to bring 2 or 3 slides for that magnetic island type observations. So here, so there's a study which I'm involved on, but majorly most of the work is done by Madison and Angel, two grad students from GMU. So I will quickly go over what they have done so far. So this, I'm not sure whether you can see that clearly in the Google Meet, but what we have is the pinching of the streamer there. So which basically kind of shows that as the streamer itself is like a current sheet, right? So it gets really extended and there might be a chance that there is reconnection taking place. And right after that pinching, so this goes with time like that. And after that pinch here, the sign arrow. So we see this feature, I'm not sure how clear it is, but when we zoom it in, what we see is an elliptical structure, and there is a cavity inside that, which basically, primarily we can say that resembles to a magnetic island. Magnetic island is basically when we have positive polarity on the top, negative polarity magnetic field lines, and they get merged together to create a current sheet, where current sheet is formed between them. And within the current sheet, there are those islands where we have null regions. So they look like something like what we have seen here in Whisper. So in comparison to that feature, there are few previous studies which have seen streamer blobs, which just looks like white blobs from Wong and Chile studies. And in and out pairs, in and out in the sense when we have reconnection taking place from the current sheet. So there are streams coming out in one direction and on the other direction. So they have seen such scenario in white light observations also. And in another study, Rapazzo has done some simulation to create how the plasmoids are generated during the reconnection and how the magnetic islands are formed. So having those in mind, the initial observations that we see here is first the pinch of streamer, which I said. Second one is elliptical shape feature moving along the streamer. And the third one is there is a clear density deficit, which we call it as cavity. So Madison and Angel have done multiple analysis methods as listed here, just to see how the projected velocities can we get from those magnetic island structures, which is developed from Weaver 2020 et al. And also this other method is to get the max point ellipse fitting. So they fit. So what we see here is the ellipse. And if we take a slit here, and from the center to the outside, if we take the line profile, it looks like that. So which basically gives a intensity profile. So taking that at all 360 degrees for that ellipse, he came up with the fitting of the ellipse on the magnetic island, and having that, he made the measurements of aspect ratio of the island. So very interestingly, what we see is the aspect ratio from the ellipse, it becomes more circular. So which basically shows that this is not just a tiny flux top or CME, which is expected to be to expand as it goes into the outside into the Ionosphere. So here we don't see any expansion as such, but what we see is this elliptical shape becomes more circular, which is usually expected in magnetic islands, right? So where we have this coalescence effect in the current sheet, where the magnetic islands merge. Initially, they look very elongated. As the reconnection process goes on, they all merge to make them more circular. So here we see something like that, which is very interesting. Another point is when we measure the velocity, they are almost like 300 kilometers per second, which indicates that they are going through along the solar wind speed, and it's not a CME which can expand with time. So it's almost the constant velocity that it continues with in the whole field of view of this one. So which shows that maybe the island is traveling in the streamer and it follows the solar wind speed, and there is a very less acceleration as what we see there. And Madison has done this analysis. What we see here is basically the sun at the center, and green is the magnetic island direction. And all the circles and ellipses that we see here are the orbits of these objects like Earth, stereo, and Whisper. And these vertical or the lines that we see here are the field of views of each instrument. So what she was trying to do is if you just first look at these two lines, is the field of view for Parker Solar Probe. So we know that these are the green points that we see in Whisper field of view. And now if we overplot that on the Stereos field of view, like core 2 and HI on the top of it, we will know whether the island is seen by those instruments or not. So having that in mind, she tried to see at those specific time intervals and specific field of views to see whether those island, so that island feature is whether seen in core 2 or H1. So we don't see a very clear very clear island with cavity, but we see like a blob type of feature. So which might be previously have misunderstood that island can be a blob itself, but here what we see is island, it looks like island in Whisper, but in core 2 or H1 it looks like a plasmoid or just a blob without any cavity. So yeah, so those are the few important results that we got from that study. So yeah, so I would stop there and
All right, wonderful. Thank you so much. So we'll take some questions. You can raise your hand online or in the room. Yes.
So you look those nested rings in the CME Whisper nested ring structure. So you're basically in that model you created, you're assuming that the flux rope, each flux surface has density, brightness. So that was the assumption in construction. So it's like you're seeing the nested
you mean in GCS data
in the grades.
here
So the grade,
with the
yeah, or whatever. This one's okay. Yeah, this. So I see. So it's basically saying, no, it's actually field lines is different, right?
Greg's online if we want to ask him to explain how they do this.
Okay, so you're assuming that you're seeing a flux surface.
So with this one, it's just a hollow tube, right? So
Yeah, I'm just saying when you see the projection, when you're assuming each field line has it.
Yeah, I'll jump in that it's important not to overinterpret this model. It's really just a geometrical demo that you can produce a lot of these forms. So I think, Shahida, you're doing it exactly the right way. You're using this as evocative of the variety of things that could be optical illusions.
But the GCS, which you did use, is a density model, right?
yes, that's right. So I'm using this just to understand the different for geometry,
Projection.
geometry, I would say. Yeah, so not for any type of physics, I would say. But with that, here I have taken different results, one with outside, and each one of them has different densities.
Okay. And then the other one, the one on the right is bent, and then this one surface. That the difference between the left and right.
It's
The
not
right one.
it's not bent, I would say. Let me tell you what
It's like different longitude.
different longitudes. Yes. Yeah.
So it's like a,
So each string here, so each one of them has different aspect ratio, right? So the one inside is the smaller one, and the one outside is the bigger one. So here, that's not what I want to see. What I want to see is if we have that flux rope, but here all of them have the same one within inside. All the heights are at one point, one longitude, right? So in that case, all the heights are at different longitudes. They are just projected on the longitudinal side, the 3-dimensional side.
So the one on the left, do they all have the same axes, the same axis?
Same axis, yes.
But the one on the right, they do not all have the same axis.
Yes. Yeah. They are shifted a bit.
Okay. Joan Burtwell has her hand up.
Yeah, hi, nice talk, thank you. When you show these pictures here of the flux rope, I would envision that as the cavity and the core of the event. Do you see the overlying coronal loop structure, or is this the leading edge of the CME?
Do you mean this one, John?
Yes, the one you have up, for example. Is there any material associated with this that's moving out ahead of it? Or is this sort of the leading edge?
So, when we see the movie, they all move together. May I know why you asked that, John? Maybe I would.
Well, I'm just trying to get a feel for, I mean, this has, as you say, it has a consistency with looking down a certain viewing angle to the axis of a flux rope. And I'm trying to figure out if the flux rope is running into the front and they're all getting smushed together, you know, that overlying arcade that is not typically part of the flux rope, the field that's anchoring the flux rope to the corona until it becomes either out of equilibrium or there's some sort of an instability. So I'm just trying to get a feel. If this is the front of the CME, then you envision a flux rope basically coming right up. The flux lines are visible right up to the top of the front of the CME. I'm just trying to get a perspective here from Whisper.
Yeah. So, Joan, I'm not sure what you mean by overlying lines that and how the flux rope is different from that. So, but here, for example, we see a different brightness happening. So that is because of it goes through a deformation at some point, and there is a high stream wind. If we look at other observations, and because of the interaction of the CME with the high stream winds, the CME front becomes deformed and becomes brighter. And but I'm not sure what you mean by the overlying.
Can I make a comment? Yeah, so Joan, like, and maybe Yuhong can comment on this too, but in Yuhong simulations, even when there's an underlying flux rope, during the eruption, that overlying front becomes part of the flux rope through tether cutting reconnection behind it. So there's not so much the situation of the flux rope sort of slamming into passive loops above it, but rather actually because of the tether cutting, the loops above it become part of a more wound up flux rope. Is that correct, Yuhong?
Yeah, the flux rope is growing. Yeah. And more actual field forms surrounding it. So, but I'm not sure about this front. Is that a parallel flux, right?
I think so. Yeah.
It's the parallel flux.
Yeah.
In front of the,
Because at the initial times, we don't see
and
that.
then they usually
Like,
curve sheet.
Yeah, there's really kind of three different things going on here, right? One of them has to do with, do you have a flux rope that kind of goes and pushes stuff along with it way down in the corona? And from what we see in erupting cavities, that doesn't seem the case. It's more that the whole cavity bodily erupts as though it's kind of taking with it any other flux above it. The second thing is the pileup of material because you have CME pushing into the solar wind in front of it. And then the third, of course, the shock, which can cause, and you can have a situation where you have isn't this right, Joan, where you can have like a shock well in front of the front, if for want of a better word, the bright structure. So there's the sheet. Yeah.
Those tend to be faint in terms of being density structures.
Yeah, but it's complicated because there's the kind of the flux rope that there's the questions of whether the flux rope formed during or was there before. And if it was there before, how does it interact during the eruption? And then there's the question of how does it interact with solar wind? And then there's the shock. And all of these will affect what we call the front or the sheath or the leading edge and the brightness of them, right?
and when we see that in white light observations, I don't know how much we can distinguish between the trend and the flux rope itself. So as per the model, going back to Craig's model once again, so we see that I can use this as a very good example. So in most of the white light observations, they almost look very clear to what we see the front of this flux rope itself.
Yeah, projections effects will intensify the cavity and intensify the front even before any of the effects like pileup.
And also the good part of the CME is we don't have any shock because it's a very, very slow CME.
That's not in there.
So no more confusions.
Other questions? Yeah.
Nice talk. I wanted to go back to the microwave flare observations.
I'm glad someone is asking for my.
The multi-wavelength is the important way to study flares. So you talked about these sources that you see in the microwave. I mean, I assume those are optically thick. But can there be multiple components along the line of sight? Is there any understanding of?
Yeah, so, and this one, once again. What we are seeing here is, so with frequency, it's like an onion peel structure, right?
Right.
So as we are going with height, we are looking at the higher and higher frequencies.
Right.
Right? So what was your question?
Well, at a given frequency, I mean, you could have
Oh, the
multiple
optical
components along the line of sight, and so your
Yeah.
mixing isn't just spatial, but you could
Yeah,
have.
yeah. So yeah, that's right. So what we are looking at the optically thick emission, right? So at each frequency, we are looking at that particular layer. So we are,
No, but it doesn't have to be one layer. You're looking
yeah,
at
that,
an integration along a line of sight that could have multiple components possibly.
yeah, so,
Hmm.
but as we are looking at this as a spectroscopy, so we are treating each frequency can be different, right? So we are basically having that line of sight effect, but depending on that frequency. Yeah, I'm not very sure how to answer this question, but
Yeah, I guess here's another way. How thick is that layer?
yeah, that's what I was
Estimated to be.
Yeah. So I'm not sure how we say that. How many? I mean, is there a band of frequencies that are integrated, and how it happens? I'm not sure. But if, for example, if we look at this example here, so we can clearly distinguish it. So here, I don't think we have more than 30 frequencies. And so each of those frequency, if we look at it in some other way, we have seen the centroids of them very distinguishedly separate from each other.
Mhm.
If you are looking at with height. So yeah, so that
So
once
it's-
again shows that how resolved we are seeing with frequency from this observation.
We have a comment in the chat from Arvind Daratha. Possibly related, you also referred to the white light integrating effect. Could you dwell on that?
Yes. Once again, the same concept, but what we spoke with radio is optically thick emission. Here we are talking about optically thin emission. So we are not seeing through in one of the cases. So in white light, what we have is the density with these observations. So as the instrument looks through at those density structures, we are just taking all the layers together and integrate them. It's not the case in radio. So in radio, they're all layers of optically thick emission. So here, as it is optically thin, so as I said before, so whatever bright structures that we see in CMEs, in the front we have solar wind and the other features. On the backside also we might have streamers. So whatever is there in that line of sight is completely integrated to show us what we are seeing here in the white light observations. Does that with respect? Yeah. So the inner field of view is around 8.5 solar radii, and the outer is around 53 solar.
53, did you say?
Okay. So it's like not accelerating anymore.
Can I ask a question about that? So you talked about looking at the shape of or watching the loops kind of move together coherently. Were they expanding as they went?
Yes.
Okay.
Yes, they do, and they expand, they unwind. Yeah.
So expanding, so do they expand basically self-similarly, do you think? And then what about the unwinding? How do you monitor that?
Unwinding, I'm yet to examine that. I just saw that when I was looking at some other feature in stereo images. So it's not seen very clearly in this, but let me play that. If we could all see if there is any unwinding. Do you see that? I see that. I actually see that.
So this is running difference, right?
This is running interruptions, yes, you're right. So so after this point, this time, the CME basically becomes pancaked, right? So let's look at this region. So here we see clockwise motion. Let me play. You see that?
I'll have to stare at it a lot more, I think. It can be hard. And how can you tell if it's unwinding versus just rotating?
Rotating. I think this thing could. If we track one bright feature, so it moves from there to there. Like that. And it's also very interesting that in Whisper, as we are seeing the same CME in opposite direction, Whisper on one side, stereo on the other side. Here we see clockwise rotation, and for stereo, it's counterclockwise. With unwinding, Sarah, it's because the radius of those rings are changing. So that's why I think that this so it expands. Maybe it's either expanding and rotating at the same time, which makes me look like it's unwinding. Right?
Well, definitely want to talk about that a little bit more later, but other questions, final questions? Okay, if not, let's thank Shahi again.